Howdy. In this video, I'm going to discuss how to use Python scikit-learn to do the support vector machine classification. Right. In the support vector machine, we were trying to divide the data or classify the data by using hyperplanes. In this very simple example, we have +1 and -1s, and the idea is to find the maximum margin linear classifier to separate these two classes from each other. As we discussed in the class, sometimes we use the kernel trick to basically separate the data by moving them to a different dimension. There are different kernel function, polynomial, radial basis function, sigmoid function, and of course the linear function that we discussed earlier, right? So next I'm gonna go to Python and do work with the Python to create a support vector machine model, right? So I have my Python data set, and initial couple of lines basically help me to clean up the data. You already are familiar with this data set, so we are using cancer research data set. And then I'm calling the pandas for data frame, numpy, from scikit-learn, model selection, train test split to divide the data. I'm setting the patient ID as the index. And if you remember, there are some missing cell values. So I'm asking, or I'm coding it to drop it from the data frame, right? And in other examples, when we did the regression model with the cancer research data, the regression model gives you a continuous number. And for that purpose, we actually introduced dummy variables to convert this class benign or malignant cancer cells to 0, 1 dummy variable, right? But in classification models, so far I've been just using the code as we have used earlier and dropping this or introducing the dummy variables, but this time I'm not going to introduce a dummy variable and just keep the benign and malignant as the class attribute, right? So let me run this first line and then the second one, so we get that warning. Actually, I should start changing this. Instead of saying train split, I could say test size, and then this would be 0.3. The same thing, it's just a complement of it, right? Once I know that, I could just go check the right, and I could also check the size of the X train length. Right, so 475 data points in it, so everything looks okay. The next is, as always, we are going to start importing our algorithm from the scikit-learn. So from scikit-learn and support vector machine, import. Right. Similar to other classification models, support vector machine can also be used for regression model as well, by calculating the probability of being in a group and then basically giving you a expected value. I'm not going to use that. As we discussed in the class, we are primarily interested in the classification model. So I'm going to just use the classification model, SVC. Support vector classification, basically, right? And let me run that line, and now I'm gonna create a support vector model, and that is going to be SVC, right? And then support vector gets a lot of parameter in it, so I can just check those parameter, but by pushing Shift Tab, right? So I can define the C value as we discussed in the class. The C value impacts the margin, right? Kernel, this is basically, as I mentioned earlier, what type of transformation it's using. This is radial basis function. If I was using the polynomial function, the degrees of polynomial would be 3. Gamma is a coefficient for polynomial, not polynomial, radial, and I believe sigmoid functions. Then there are other parameters as well that I could set it up, right? And for C, it is 1 to any number, basically. Kernel, we have linear, polynomial, radial, and sigmoid functions. So I can use one of them. To begin with, I'll just go with saying kernel equal to sigmoid, right? And then C1 was default, but I will still write it in case I want to change it. And then a gamma value, I'm gonna just say auto, right? And then next I'm gonna train my model, actually fit my model, right? Dot fit, and to fit, I'm gonna write X train and Y train, right? So it looks like everything worked just okay. And at this point, I need to know what is the basically performance of this port vector machine. For that, I can look at a couple of things. I can look at the accuracy score, confusion matrix, and so forth. So I will just start importing them as well from metrics, scikit learn metrics, import confusion matrix. I'm saying why I'm not getting this confusion matrix. And then I'm gonna also do the same thing for accuracy score, right? So those two are in the memory. So let me go check the confusion matrix first, right? And for the confusion matrix, I need to give the true and prediction. My true values are basically the Y trains, and my predictions are going to be SVM model, and I will call the prediction predict, and then I'm gonna call X train, right? It's basically no for the class, right? So what does this mean? Basically this 167, this columns are predictions and then the rows are actual. So basically it says there were 167 observation. I predicted they are benign, and they were actually benign as well. And then there were 145, they were malign. I predicted they were malignant, but in reality they were benign, right? And overall, if I look at my accuracy score for the same data, that's 35% accuracy. It's not very good. Let me check the training data as well, validation data as well. Y validation, X validation. Similarly, not that good. It seems I'm not able to predict the malignant correctly when it is really a malignant. Like you see it is 0, 0 with this model, and I believe if I have the accuracy, I will end up something around the same numbers. It is 33% on the validation data. Either way, this is not a good model. Of course, I could go update this one. let me copy this and kind of experiment with it, because otherwise when I post this code, you may not be able to see it. So I'm going to convert to a linear kernel and run it. And then let's check the confusion matrix for it, right? Suddenly this is much better. So I had 163 misclassification and 145 misclassification. Basically these are benign when it was actually malignant, right? And then this 163, I was thinking they are benign, but they were actually malignant. And then there were 145 of them. I was thinking they are malignant, but they in fact were benign type of cancer, right? So this time it's significantly improved, and I can check the accuracy score for it as well. Right, so 97%. Similarly, I can look into the confusion matrix for the validation data and accuracy score for validation data as well, right? Oops. Apparently I wasn't able to copy this thing. Right, so everything has improved a lot just because I changed the kernel from sigmoid to linear. I could also change the other parameters, but at this point I am not going to do basically manual setup. Instead, I will go and start creating a loop and then solving through the loop. As I mentioned in the class, creating for loops to find the best parameter is kind of old school. In this video later, I will also use grid search to get the best parameter set for the SVM as well, right? So if I go to this function here as a support vector function and look into it by shift tab, I see that I could change the kernel, gamma, coefficient, degrees, some other parameters as well. Decision function shape. This is important, especially when we are doing multiple classification groups, more than two. Let's say I had 3 types of cancer or n type of categories. This is basically says one versus rest. So when it is comparing or creating this solution, it checks this, let's say this subset versus the rest of the data, right? The rest of the categories. And then there is the other option is one versus one. In that case, you basically do compare, kind of ignoring the rest of the data, just looking at, let's say 2 types and then the other 2 types and then the other 2 types, rather than one versus every other type out there. Right? I believe OVR is default for the one-to-many as well, right? So I can check these and try different numbers like C value, RBF, degrees of freedom, gamma, and so forth. So let's create that loop or process we have done in the class. So first thing is the kernel, right? I'm gonna have this kernel and I will say I have kernels, and I will copy paste actually. Let me not type all of them here. Where are the kernels? Right, so there are 4 kernel types. I'm gonna try all. Right, next I'm gonna define a range for the C, right, and that is np.arange, right. Let's say 1 to 52 with an increment of 10. I will also define a range for the degree. That was another parameter here, right? So I'm gonna do kernel, degree, gamma, and coefficient, and C, of course, the one I have already started. So let's say range and degree is equal to, I'm gonna just copy paste this one and change it quickly. that is the polynomial degree, right? It will only impact the polynomial kernel function, right? And then I would say range for coefficient, right? And for that, I'm gonna choose something between 0.001 and let's say 10 with an increment of 0.5. I'm just making up these numbers, by the way. There's no meaningful way. If I was trying to find the best parameter set, and if I had enough time, I would probably look even a bigger range for the C degrees and coefficient, right? And then I'm going to create another one for the gamma, and that is in the gamma it says there are two types basically, degree gamma, so I can use polysigmoid, right? So it gamma impacts these three basically for the coefficients. And if I can find, there is auto and there is scale, so I'm gonna use both of them, right? So I will try both versions, right? And let me run this one, and next I am going to create the basically if loops, for loops to determine the best set of parameters. So first, for I in KRN, right? For J in range C, for K in range degree, let me just follow the order I had above, for Z in range that is co, and for X in range gamma, right? Once I have this, I'm gonna now basically call my CVM model that I just created here, feed all those parameters, then fit, and then calculate the accuracy score, and finally keep the best parameter set, right? So let me do this. So kernel is I, then I have the C is J, then degree is equal to K, then I said coefficient 0, that is basically Z, and finally gamma is equal to X, right? I, J, K, Z, X. So it's gonna try all those combinations and get me the best result using the training data set. But as we did in the class, once I'm done with the training, I'm gonna actually test the accuracy on the training validation data set, right? I'll say accuracy score is equal to accuracy score on the validation data set, right? And then if my best score is less than the accuracy score I just calculated, that means the new accuracy score is better. So I'm gonna update my best score to accuracy score, right? I will also collect at this point what is the best I, that is I, best J is J, best K is K, best Z is Z, and then the best X is X, right? And finally, once I'm done with all, I'm gonna print this result for my evaluation. So I will have the best score, then best I, best J, best K, best C, and best X. Right. So let's run this one. Oh, we check. Right, here it is. This is supposed to be auto, not the other way. All right, let's try. Run. It took about 2 minutes on my computer to get through this loop. So basically what we are doing is like 4 different kernel function, 5 different C value, 5 different range, and so forth. We are solving this problem about 4,000 times. So that is a lot of calculation here. And although each one of them does not take much time, doing it 4,000 times is a lot, right? So at the end, basically it says the best validation score is 0.97549. Radial basis function is the best one with the C value of 1. Polynomial function degrees 3. And then coefficient of 0.01 and scaling as the gamma, right? With those, I get this result. And that is good. And it is also nice, but I had to type so many basically for loops, and I could also go through other calculations as well. So this could be a little bit troublesome. So in that case, a better method is to use actually the grid search, which basically does this search for you and gives you the result, right? So let's do the grid search. And this time I'm gonna import the model selection, right? And import GridSearchCV. And I'm gonna also, let's do this one as a line, right? Next, for the grid search, I need to define the list of parameters, right? So I'm gonna create an list and call this as parameter. This is curly brackets, by the way. First is the kernel, right? And the kernel, as it is typed in this model right here, it needs to be the same typing. So it is, if you put a different spelling or change the case to a lowercase to a capital letter and so forth, it's not gonna work. It needs to be exactly the same term. So kernel, and I'm gonna check all these for the kernel, right? And that is this time a list, and here's it. And then I'm gonna look into the C values, right? C, and that is going to be equal between 1 and 52. I think that's what we said earlier, if I can, right? With an increment of 10, comma. Then I had degrees, right? And for that, I'm gonna say degree. All right, and that is basically a list of 3 to 8, comma. Then I had the coefficient, and coefficient is coefficient 0. And for that, I have the list of in the following format. It was 0, 0, 1 to 10 with an increment of 0.5, right? And finally, I had the gamma, and that was basically between auto and scale. I could just, add this continuously after each other. I list it this way to just make it easy to read it, right? So I created this parameter, all right? Next is I'm gonna call my CVM model again. I could also name as a different one, but I'm using the same thing. SVC, right? So that is what it is. And now I can call my grid search as a name, and this is GridSearchCV, right? I'm gonna do the GridSearchCV on my CVM model, right? And I'm gonna use the parameters, that param list. And finally, GridSearch itself has its own parameter set, right? So I could set all these things, and I'm gonna just select the CV, right? And CV is the basically cross-validation, and I will do cross-validation, let's say 5 times, right? Basically, it is sampling 5 times to make sure that this model is working properly, right? All right, actually I could just do the fit as well, right? This time I'm gonna say grid search fit, right? Again, the fit function is you will provide the x value first and then the y, right? X train, y train, right? So now it is basically going through all this parameter list as we did here for the for loops, and at the end it's gonna give us the list of best parameters, right? One thing, this took about 10 seconds compared to 2 minutes of the earlier one, right? So I got the result already, and I'm gonna check basically the parameters, and for that you use the grid as right dot best parameters, right? So here's my best parameters. C equal to 1, coefficient is 0.01, degree is 3, gamma is scale, kernel is RBF, and I believe that is exactly what this model said earlier, right? So we also printed the accuracy, but it is RBF scale, right? And scale is there, 3 is there, 0.01 is there, and the 1. Right, so we got basically the same set of parameters that we did earlier by writing so many for loops. In this case, I just define a parameter kind of list, and within that list, grid search enumerates all of them and gives you the best result. Right, so I can go create this model now. For that, I need to copy basically these 3 lines. All right, add it here. Kernel is RBF. J is equal to 1. Degree is 3. Coefficient is 0.01. And gamma is scale. Right, let me run it. All right, so that I believe the same number as well, 14, 13, right? So this is the number I got. Again, because I have the best parameter, of course, I'm expecting to have the same result, right? So this is basically how we do the grid search. It is much more efficient than using these all for loops.